On May 14th, astronomers at the Minor Planet Center updated the approach geometry for an object larger, brighter, and closer than the interstellar candidate everyone has been tracking. It's not 3I Atlas. It's coming for Earth next week, and until 48 hours ago, most of the public had no idea it was inbound. Here's what you need to know right now. A comet designated C-2025 K1 Atlas has been revised from a distant past to a near-Earth flyby scheduled for May 22nd, peaking at roughly 1.3 million kilometers. That's about 3 times the distance to the moon. It will not hit us. What changed is the orbit solution. Fresh astrometry from observatories in Chile and Australia tightened the path, and the new numbers show K1 swinging much closer than the preliminary track suggested. At the same time, brightness reports jumped half a magnitude in 72 hours, putting the comet near magnitude 6 right now, within naked eye range under dark skies, in climbing. For context, 3I Atlas, the object some researchers suspect arrived from beyond our solar system, sits around magnitude 9 and isn't expected to brighten much more. C1 2025 K1 is already brighter, bigger in apparent size, and on a collision course with our neighborhood. By collision course, we mean a very close pass, not an impact. Language matters, and so does precision. Today you're going to learn exactly what C-2025 K1 is, why the orbit changed, what the latest data from ground observatories and NASA's solar monitoring fleet tell us, why having multiple unusual objects inbound at the same time raises eyebrows, and what you can see with your own eyes between now and closest approach. Everything in this script is drawn from public databases. The Minor Planet Center, JPL's small body database, the Central Bureau for Astronomical Telegrams, SOHO and stereo spacecraft telemetry, and reports filed by professional and amateur observers worldwide. No leaks, no unnamed sources, just published numbers and images anyone can verify. Let's start with the confirmed facts. C-2025 K1 was discovered on March 19th by the Atlas survey in Hawaii. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes scanning for near-Earth objects. The initial orbit fit was rough because the comet was faint, around magnitude 14, and the arc of observations was short. Early calculations placed perihelion, the closest point to the Sun, at 0.9 astronomical units, well inside Earth's orbit, but not intersecting our path. The preliminary estimate for Earth approach distance was listed as 9 million kilometers, far enough that it didn't trigger any close approach flags. That number sat in the database for 6 weeks while K1 crept sunward and brightened steadily. Then on May 12th, observers at Cerro Tololo in Chile and Siding Spring in Australia both imaged the comet in measured precise positions. When those measurements were folded into the orbit calculation, the solution shifted. Perihelion stayed roughly the same, but the orbital inclination, the tilt of the comet's path relative to Earth's orbit, changed by nearly 2 degrees. 2 degrees sounds tiny, but at interplanetary distances, it translates to millions of kilometers. The revised close approach distance dropped from 9 million kilometers to 1.3 million. Suddenly, C-2025 K1 went from a routine comet to one of the 10 closest comet flybys recorded in the last 2 decades. Close approaches happen. Most pass without incident. What makes this one unusual is the timing and the brightness curve. Magnitude 6 already, 9 days before closest approach, means K1 is either bigger than average, more active than average, or both. For comparison, a typical comet at 1.3 million kilometers might reach magnitude 7 or 8. K1 is outperforming expectations, and it's still approaching. If the trend holds, it could hit magnitude 4 or even 3 at peak, making it easily visible to anyone who knows where to look, even from suburban skies. That would put it in the same visibility class as Comet Neowise back in 2020, the last comet that genuinely stopped traffic. Now let's talk about what changed in the last couple of days beyond the orbit. Brightness isn't the only story. Images from the past 72 hours show the tail lengthening and a secondary feature developing. The main dust tail extends roughly 2 degrees, about 4 moon widths, stretching away from the Sun as expected. but a fainter, narrower spike appeared on May 13th, pointing in a slightly different direction. That's almost certainly an ion tail, made of charged gas pushed by the solar wind rather than sunlight pressure. Ion tails mean the comet is venting gas, not just dust. Gas activity often spikes as a comet nears the sun, and heat breaks down ices below the surface. Water, carbon monoxide, carbon dioxide all start to sublimate and stream away. The fact that we're seeing both tail types suggests K1 has a healthy supply of volatiles and is responding strongly to solar heating. Spectroscopy, the analysis of light broken into colors, hasn't been widely published yet, but two teams have posted preliminary results. One group in Spain detected strong emission lines from cyanogen, a molecule made of carbon and nitrogen, and another from diatomic carbon. Both are common in comets. What's less common is the intensity. The cyanogen line is reportedly stronger than expected for a comet this far from the sun. K1 is still outside Earth's orbit, yet it's already outgassing like something much closer. Does that mean the nucleus is unusually rich in CN-bearing ices? Or that it's smaller and heating faster? Or that we caught it during a sudden outburst? We don't know yet. More observations over the next week will clarify whether this is steady activity or a temporary flare. Here's the geometry in plain language. C2025 K1 is diving in from the outer solar system on a steeply inclined orbit, tilted about 38 degrees to the plane where Earth and most planets travel. It's coming from the direction of the constellation Sculptor in the southern sky, swinging up and inward. Perihelion occurs on May 27th at 0.89 astronomical units from the Sun, just inside Earth's orbit. But K1 crosses Earth's orbital plane on May 22nd, and on that date we happen to be nearby. Not directly in the path, but close enough that the comet passes within 1.3 million kilometers. The encounter is fast. Relative velocity at closest approach is about 42 kilometers per second. The comet spends less than 12 hours inside the moon's orbit, then climbs away to the north. By early June, it will be receding, fading, and lost in evening twilight for Northern Hemisphere observers. Now, why does having multiple unusual objects inbound at once matter? It's unusual but not impossible. Right now, we're tracking 3I Atlas, the interstellar candidate with a hyperbolic orbit that some researchers believe originated outside the solar system. We're watching C2 and C25 R2 Swan, a sun-grazing comet discovered by the SOHO spacecraft. We have 240P NEAT, a periodic comet making a moderately close pass, and now C2025 K1, revised to a very close flyby. 4 objects, 4 very different orbits, all reaching interesting points within a 2-week window. Coincidence or pattern? The honest answer is coincidence is perfectly plausible. Comets don't coordinate. Discovery timing often clusters because surveys ramp up observations when conditions are good, and May offers long, dark nights in the southern hemisphere where many surveys operate. But the human brain loves patterns, and when you see multiple objects arrive together, it raises questions. Are we passing through a region of space with more debris? Did a larger body break up in the past, scattering fragments on similar but not identical paths? Or is this just selection bias, the fact that we notice clusters more than we notice gaps? What does this mean for science? A comet passing this close offers a rare chance to study composition, structure, and activity up close without sending a spacecraft. Ground-based radar might be able to ping the nucleus if it's large enough, giving us size and shape data. Infrared telescopes can measure temperature and dust production rates. Ultraviolet instruments can track the hydrogen cloud that surrounds active comets. And if K1 continues to brighten, even small backyard telescopes will capture enough light to analyze the gas emissions. Close flybys also test our models. Did we predict the brightness correctly? Does the tail behave as simulations expect? How does the solar wind, especially during solar maximum when the sun is active and turbulent, shape the ion tail? Every close comet is a natural experiment, and K1 is giving us front row seats. For space weather watchers, the timing is notable. We're near the peak of solar cycle 25. The sun is throwing frequent coronal mass ejections, bursts of magnetized plasma that ripple through the solar system. When a comet's ion tail intersects one of those CMEs, the tail can twist, break, or flare dramatically. We saw this with other comets during active solar periods. Stereo and solar orbiter spacecraft are positioned to catch any interaction between K1's tail, hull, and solar outflows. If a CME hits the comet around closest approach, the show could be spectacular, and the data could reveal how solar storms interact with small bodies in real time. That's not speculation, that's just watching for an event that happens regularly, but is rarely this well observed. Now let's file the anomalies, the things that don't quite fit the standard comet profile. First, the brightness surge. K1 jumped half a magnitude, roughly 60% brighter, in 3 days. Comets do flare, often because a fresh patch of ice gets exposed or a pocket of gas bursts through the crust. That's the likely explanation here. What some speculate is whether the flare was triggered by a collision with a meteoroid or another small fragment in the same stream. No evidence supports that yet, but if the brightness jumps again or fluctuates irregularly, it would hint at something more than smooth out gassing. Second, the orbit revision itself. A 2-degree shift in inclination after 6 weeks of tracking is larger than usual for an object this bright. Normally, orbits converge quickly once you have dozens of observations. K1's orbit took longer to settle. One natural explanation is that the comet was faint early on, so positions were less precise, and the extended time frame let small errors accumulate. Another is that non-gravitational forces, the tiny pushes from jetting gas, altered the path slightly. Comets aren't inert rocks, they're active engines, and every jet acts like a tiny thruster. If K1 started out gassing earlier than models predicted, those forces could have nudged the orbit just enough to surprise us. What we don't know yet is whether the current solution is final. More observations this week will either confirm the 1.3 million kilometer flyby or tweak it again. Third, the double tail structure appeared very suddenly. Ion tails can switch on fast when solar wind conditions change, but the images from May 10th show only dust. By May 13th, the ion spike is clear. Did the solar wind intensify, or did the comet's gas production jump, or both? Solar orbiter data from that window haven't been fully released, so we can't yet correlate the tail onset with a specific solar event. Some observers noted that the ion tail angle doesn't perfectly align with the Sun-comet line, which is unusual. Magnetic fields in the solar wind can bend ion tails, especially near solar maximum, when the interplanetary field is tangled. That's the mainstream explanation. A speculative angle, and it's only that, is whether K1 flew through a boundary in the solar wind, a region where fast and slow streams collide, creating turbulence that shaped the tail asymmetrically. We'll know more when Solar Orbiter and Parker Solar Probe data are published. Fourth, and this is the one that gets whispers on the observer forums, K1's color. Early photometry suggests the coma, the cloud around the nucleus, is slightly redder than average. Most comets are neutral or slightly blue due to gas emissions. Reddish tints usually mean more dust or organic compounds. Organic-rich comets aren't rare, but combined with the strong cyanogen signal, it raises the question of composition. Is K1 a typical Oort cloud comet, or did it form in a colder, more carbon-rich region? Could it even be a chunk of a larger body that broke apart long ago, carrying a different chemical fingerprint? All of that is speculative. What's confirmed is the color measurement. What it means will take lab analysis of the spectra in comparison with other comets. Between now and closest approach, visibility is excellent for southern hemisphere observers and challenging but possible for northern skies. Right now, May 15th, the comet is located in eastern Sculptor, rising a few hours before dawn. From latitude south of the equator, it's well placed in a dark sky by 4 a.m. local time. Look toward the southeast. If you have dark skies and know the star patterns, you might spot it as a faint, fuzzy patch without optical aid. Binoculars make it easy. 7 by 50 or 10 by 50 glasses will show the coma in the start of the tail. A small telescope reveals more detail, but don't expect Hubble images. You'll see a glowing head and a delicate streak. By May 20th, the comet climbs higher and brightens further. Estimates put it at magnitude 5, comfortably visible to the naked eye from rural locations. The tail should stretch 3 to 4 degrees, roughly 6 to 8 moon widths. That's enough to be photogenic. If you have a camera with a decent lens, a tripod, and a few seconds of exposure, you'll capture it. Closest approach happens early on May 22nd. At that point, K1 will be moving noticeably against the stars if you watch over an hour or two. The motion isn't dramatic like the moon, but it's detectable. For Northern Hemisphere observers, the comet stays low. Best views come from southern states or countries closer to the equator. If you're north of 40 degrees latitude, you'll need a clear southeastern horizon and might only catch it in twilight. After May 22nd, the comet pulls away and fades. By the end of the month, it drops back below naked eye visibility. The window is short. If you want to see this one, plan for the nights of May 20th through 24th. Weather permitting, that's your chance. No special equipment required. Just clear skies and a willingness to wake up early or stay up late depending on your longitude. Now the reality check. What's solid? C-2025 K1 is a real comet with a confirmed close approach of approximately 1.3 million kilometers on May 22nd. It will not impact Earth. The current brightness is around magnitude 6 and rising. The orbit is well determined based on multiple observatories, and barring a major non-gravitational surprise, the close approach distance won't change significantly. The comet shows both dust and ion tails, indicating active outgassing. Spectroscopy confirms typical cometary molecules with stronger than average cyanogen emission. All of that is observational fact. What's likely? K1 will continue to brighten as it nears Earth and the Sun, possibly reaching magnitude 4 or 3. The tail will grow. Observers with even modest equipment will see it easily. The comet is probably an Oort cloud visitor, a chunk of ice and rock from the deep freeze beyond Neptune, nudged inward by gravitational perturbations thousands of years ago. The brightness surge is most likely a natural outburst triggered by subsurface ice exposure. The orbit shift reflects improved measurements, not a fundamental mystery. The double tail is textbook comet behavior under solar wind influence. What would count as a true breakthrough? If radar observations reveal the nucleus is far larger than brightness suggests, implying an unusually dark surface. If spectroscopy finds molecules that don't fit solar system formation models, hinting at interstellar origin or exotic chemistry. If the brightness curve does something truly bizarre, like dropping suddenly or spiking far beyond predictions, suggesting fragmentation or a collision. If spacecraft data show K1 interacting with the solar wind in a way we've never seen. Any of those would be major news. None are indicated by current data. We're watching a close, bright, well-timed comet, and that alone is gift enough. So why the alarm? Why the title about something bigger coming for Earth? Because for the general public, 3I/Atlas has been the headline object, the mysterious traveler, possibly from another star. It's exotic, it's uncertain, and it's been the focus of speculation for weeks. But in terms of size, brightness, and proximity, C-2025 K1 dwarfs it. K1 is the bigger story for anyone who wants to actually see something, photograph something, and experience a close comet firsthand. 3I Atlas is a faint dot requiring serious optics and tracking. K1 is a naked eye object passing closer than almost any comet in recent memory. Bigger, brighter, closer. That's not hype, that's the numbers. Watch the brightness reports over the next 72 hours. If K1 jumps another half magnitude, we might be looking at a magnitude 3 comet by closest approach, rivaling the brightest comets of the last decade. Watch for updates on the orbit solution. The Minor Planet Center typically releases revised elements when new observations come in. Watch solar activity. If a coronal mass ejection launches toward K1 around May 21st or 22nd, the ion tail could put on a dynamic show. And watch the southern pre-dawn sky. This is one of those rare times when the data and the sky align to give us something memorable. One last thing. The conversation around 3I Atlas and interstellar objects isn't over. Even as K1 steals the spotlight, teams are still refining the trajectory and composition analysis of the Atlas candidate. If it's confirmed as interstellar, that's a historic first for an object discovered inbound rather than on the way out. But science doesn't demand we choose one story. We can watch both. We can appreciate the exotic mystery of a possible visitor from another star and the visceral thrill of a bright comet racing past Earth close enough to study in detail. Both matter. Both teach us something. And both remind us that space is not static. It's crowded, dynamic, and full of objects on paths we're only beginning to map. 2025 K1 Atlas is coming, and next week it will dominate the sky for those who look. The countdown is on, and the next chapter of this encounter unfolds in real time. If you want to catch the next update as brightness peaks and closest approach data rolls in, make sure you're subscribed so you don't miss what happens when a comet and a planet play celestial near miss.